Let's get into it. Number 10. Meteorite impact flashes. You're looking out a tiny window as Orion swings behind the moon and the dark swallows the surface. Tiny white pinpricks erupt across the black plane in instant sparks that vanish before the camera can catch them. The crew reported 6 flashes in hours. Mission Control answered with silence, then cheers. The moon has no atmosphere, so even the smallest bits of rock strike the ground and vaporize, producing brief, bright flashes. That's normal, but the odd part is frequency. Models predicted a slow trickle. The astronauts saw a burst. If these strikes cluster in certain regions, future habitats could face a steady rain of micro-impacts. One view is that human eyes spot, transients cameras miss. Another is that a recent impact kicked up a short-lived cloud of ejecta. No one has a final count yet. Back on Earth, teams used the Lunar Reconnaissance Orbiter and the new Impact Flash program to pin down where each bright dot came from. Cameras often missed the strikes because they were too fast. Human eyes saw what shutters could not. If micro-impacts are more common than models say, engineers must redesign habitats and suits for a much harsher environment. Thick shielding adds mass. Mass means more fuel and more cost. Some engineers now talk about building inside lava tubes or using regolith berms for natural protection. Others want networks of ultra-fast detectors and automated shutters that can catch transients humans miss. NASA hasn't declared an emergency. The agency calls the results preliminary and promising for science. Still, there's a practical urgency. We're planning to live on this world again. The flashes were a reminder. The moon isn't simply a museum. It's a place that still changes under our feet. Number 9. The moon is shrinking. That sounds like a headline from a tabloid, but it's measured, published, and real. The moon's interior is cooling. As it cools, the entire body contracts, and over the last few 100 million years, the diameter has lost roughly 150 feet. That doesn't sound like much until you think about what happens to a brittle shell when the inside pulls away. The crust can't flex. It cracks instead, shoving slabs of rock over each other and building cliff-like ridges called lobate thrust faults. The Lunar Reconnaissance Orbiter has mapped thousands of them, and many are young by geological standards. A January 2024 study led by Tom Waters at the Smithsonian found lobate scarp sitting inside candidate landing zones for Artemis 3, including the Djurlash J-Drimsrim 2 region near the South Pole. Those faults aren't dormant scenery. When they slip, they produce shallow moonquakes. Unlike earthquakes that last seconds, moonquakes can roll on for hours because the dry, fractured crust rings like a bell. Apollo seismometers recorded quakes that shook for over an hour. The surface is covered in loose regolith, and on steep slopes even moderate shaking can trigger landslides. Shackleton Crater, one of the most studied sites for a future base, has exactly those slopes. For a short visit, the odds of a damaging quake are low. For a permanent outpost, the math changes. The cumulative risk grows with every month of occupation. EnView's engineers now face a question Apollo never had to answer. How do you build on ground that may shift without warning and keep shaking long after the first jolt? Nobody has a standard answer for that yet. NASA says the findings don't cancel plans, but they do mean rethinking where and how we build. The moon isn't dead rock. It's still contracting, still cracking, and still capable of shaking the ground under an astronaut's boots. Number 8. The missing water paradox. The moon's south pole is cold. Temperatures inside permanently shadowed craters drop below -400 degrees Fahrenheit. At those temperatures, water ice should accumulate over billions of years, layer after layer, building thick, bright deposits, the way it does on Mercury and on the dwarf planet Ceres. But when NASA's ShadowCam peered into those eternal shadows with the sharpest resolution ever aimed at the lunar poles, it found almost nothing. No widespread sheets of frost. No thick, bright ice fields. Just patches, thin and scattered, far less than models predicted. That's the paradox. Mercury is closer to the sun and bakes at temperatures that would melt lead on its day side. Yet Mercury's polar craters hold nearly pure ice. The moon is colder, farther from the sun, and should be better at trapping water. Somehow it isn't. Scientists at the University of Hawaii published a study calling it a genuine mystery. The leading idea is that meteoroid impacts churn the top layer of soil and bury or destroy ice before it can build up. Another possibility: the moon's axis has shifted over billions of years, a process called true polar wander, meaning craters that sit in permanent shadow today were once exposed to sunlight that boiled their ice away. A third suggestion: many of these craters are geologically young, less than 2.2 billion years old, meaning they haven't existed long enough to collect ancient reservoirs. NASA chose the South Pole partly because planners assumed water would be accessible. Water means drinking supplies, breathable oxygen, and rocket fuel made from local resources. If the ice is thinner and patchier than expected, the economics of a lunar base shift hard. Harvesting enough water could require processing enormous volumes of regolith. That means bigger machines, more power, and more mass launched from Earth. The whole promise of living off the land depends on water being there in usable amounts. No one can say whether the ice is truly scarce on the surface or just buried deeper where cameras can't see. The only way to know is to land, drill, and measure. That's one reason Artemis 3 aims for the South Pole. Whether the moon becomes a fuel depot for deep space or just a very expensive campsite depends on what those drills find. Number 7. Glassy lunar deposits. You peer at a patch of lunar ground that shines like broken mirror under low-due sun. Volcanic glass? Impact melt? Both are possible. Here's how to tell. Glass on the moon forms when rock melts and cools fast. That happens during big impacts or long ago volcanic eruptions. The crew recorded smooth, localized patches on the far side that stand out from nearby rock. Two main views compete. One says these are ancient glass pockets preserved by cold and lack of weathering. The other says they're younger, created by recent impacts that splashed molten rock and left fresh glass. If they're young, the moon has been geologically active more recently than textbooks say. That would change landing site choices and where we search for resources. Researchers will compare Artemis photos with high-resolution orbital spectrometers and plan targeted lander visits. For people planning lunar bases, the practical questions are immediate. Where is the safest ground? Where are the best science targets? And how do we build without disturbing fragile, informative sites? Some researchers, like the team at Brown University studying lunar silicates, hope these glassy patches will contain trapped volatiles or records of past impacts hidden from orbital view. Others warn that fresh glass could mean active processes that add risk. The moon may be quieter than it looks, or it may be more active than we thought. Number 6. Micrometeoroid density spike. The cabin sensors began to ping more often than engineers expected, tiny impacts registering as brief, sharp signatures against the quiet background. Orion had crossed a patch of space where particle hits jumped for a short time. The easy answer is you pass through a debris stream. That happens. The worrying part is the pattern didn't match any known meteor shower or predicted debris track. Models said one rate. The instruments showed a burst. If small debris clusters exist near the moon more often than we thought, shielding plans must change. Thin skins and light armor used for probes won't protect habitats. Engineers are already rerunning shielding models and considering layered or buried structures for long-term bases. Possible causes include recent fragmentation of a small asteroid or fresh ejecta from a nearby impact that lofted debris into a temporary cloud. Another idea is electrostatic lofting of dust near the surface that the spacecraft intersected. Every possibility demands different fixes and different costs. Teams on the ground are combing through timestamps, orbital geometry, and other spacecraft data to find the source. They synced timestamps between Orion, the Lunar Reconnaissance Orbiter, and other satellites to see if a recent impact could have thrown up a cloud of debris. A tiny crater appeared where a flash was reported. That supports the fresh ejecta idea. Other data suggested a short-lived stream unrelated to any single crater. That points to a fragmenting rock that broke apart in lunar orbit and spread shards along a path. A fragment cloud means temporary local danger that fades. A steady stream or frequent clusters means a persistent hazard that forces different building choices. Engineers are already sketching solutions. Bury habitats under meters of regolith, build inside lava tubes, use layered shielding that can be repaired on site. All of those cost mass and money. Scientists will keep comparing records and modeling particle trajectories. Humans can survive on the moon. But surviving cheaply and comfortably depends on knowing how rough space really is. Number 5. Shadowed crater glows. The crew watched a dark valley along the Terminator, and for a moment faint patches lit up where no sunlight should reach. The astronauts reported a soft, steady shimmer that didn't match camera noise. 3 mechanisms are in play. Electrostatic levitation happens when sunlight and the solar wind charge tiny dust grains until they float, scattering any stray light. Volatile release means trapped gas warms and vents, carrying dust that makes a brief haze. Or charged particles might be focusing into a glow, similar to auroras on Earth, but driven by weak crustal magnets on the moon. Moving dust ruins, seals and scours optics. Outgassing changes local conditions near a habitat. Teams on the ground are matching the crew's timestamps to orbital spectrometers and magnetometer maps to see which mechanism fits. If floating dust is the cause, spectral signatures will show broad scattering and a weak thermal signal. If outgassing is the cause, traces of water or other volatiles might appear in the spectra and in gas instruments aboard orbiters. If charged particle focusing is the cause, maps of crustal magnetic anomalies should line up with the glow locations. Engineers are listening because the stakes are practical. Dust that floats will abrade seals, clog filters, and coat camera lenses. Vents and suits could fail faster than planned. If gas pockets vent unpredictably, that changes where you place a landing pad or a habitat airlock. The next steps are simple and careful. Point high-resolution spectrometers at the same spots, run particle and dust models, plan a robotic scout to sample the area. None of this is dramatic science fiction. It's hard work, and it's urgent. If the moon vents gas or levitates dust, we need to know before we build there. Number 4. Unexplained magnetic ghosts. The moon has no global magnetic field. Its core is too small and too cool to drive a dynamo the way Earth's liquid iron core does. Without a magnetic field, the surface is naked, bombarded by solar wind and cosmic rays with nothing to deflect them. That's the textbook answer. But the textbook has a problem. Scattered across the lunar surface are patches of magnetized rock, localized magnetic anomalies that behave as if something magnetized them and then walked away. They exist on a world that shouldn't be able to create them. Apollo astronauts brought back rocks with remnant magnetism baked into their crystals. For decades, scientists assumed those rocks recorded a long-lived global field that died billions of years ago. New research upended that story. A 2024 study found that the Apollo samples came from titanium-rich regions where volcanic eruption triggered brief, intense magnetic spikes lasting only thousands of years. Not a sustained dynamo, just flashes. That explains some of the magnetism. It doesn't explain the far side anomalies. On the opposite side of the moon from giant impact basins like Imbrium and Serenitatis, there are concentrated magnetic patches that line up suspiciously with the geometry of those ancient collisions. One theory says the impacts created clouds of superheated plasma that briefly amplified a weak background field and stamped a magnetic signature into the crust on the far side. Another theory points to subsurface magma, cooling slowly enough for minerals to align with whatever faint field existed at the time. These magnetic patches interact with the solar wind and create mini magnetospheres, tiny shields that deflect charged particles away from the surface directly beneath them. That sounds protective until you realize the deflected particles pile up at the edges, creating radiation hotspots right next to shielded zones. An astronaut walking across a magnetic boundary could go from a relatively sheltered area to a concentrated radiation zone in a few steps without any visible warning. Orbital instruments can't map these fields at fine enough scale. NASA's planned Lunar Vertex mission will land a rover at the Reiner Gamma Swirl to measure the magnetic field at ground level for the first time. Until then, Every Artemis surface walk near a magnetic anomaly carries uncertainty. The moon's invisible magnetic ghosts are real. We just don't know exactly where they begin and end. Number 3. The dust that hunts you. Before the first Apollo crew came home, engineers already knew something was wrong with the dust. It clung to everything. It worked into seals. It scratched visors. Harrison Schmitt, the geologist on Apollo 17, breathed it inside the cabin and said it smelled like spent gunpowder. His throat burned and his sinuses swelled. He called it lunar hay fever. That was 2 days on the surface. Artemis plans weeks and eventually months. The problem isn't just that lunar dust is annoying. It's that lunar dust is fundamentally different from any dust on Earth. There's no wind, no water, and no weathering to round off the edges. Every grain is a tiny shard of glass and mineral, jagged and sharp at the microscopic level, formed by billions of years of meteoroid impacts, grinding rock without erosion to smooth it. Those shards are small enough to penetrate deep into lung tissue. Studies at the European Space Agency found that simulated lunar dust can damage lung cells and brain neurons in ways similar to toxic industrial particles. The comparison scientists reach for is asbestos, not because the chemistry is the same, but because the shape and size let the particles lodge where the body can't clear them. Now here's what makes lunar dust unlike anything else. It moves on its own. The moon has no atmosphere, but it has a faint, strange glow along the horizon at sunrise and sunset. Surveyor landers photographed it in the 1960s. Apollo astronauts sketched it from orbit. For decades, no one could fully explain it. The best guess right now is electrostatic levitation. Ultraviolet light from the sun strips electrons from dust grains on the day side, giving them a positive charge. Grains in shadow keep their electrons and stay negative. At the boundary between light and dark, the charge difference launches particles off the surface. Some float centimeters. Some may reach kilometers in altitude. That means dust isn't waiting passively on the ground for an astronaut to kick it up. It's already airborne, riding electric fields across the terminator, coating anything in its path. Solar panels lose efficiency. Camera lenses fog. Thermal radiators that need to shed heat get insulated by a film of clinging particles. Apollo missions lasted days, and the dust damage was already serious. Suit joints stiffened, seals wore down. One astronaut reported that another few days would have compromised his suit's pressure integrity. For long-duration Artemis missions, the engineering challenge is enormous. NASA is testing electrodynamic dust shields, surfaces that pulse with electric current to repel charged particles. Some work in the lab. None have been proven on the moon. Other teams are designing airlocks that keep dust outside the habitat entirely using brushes, vacuums, and magnetic traps. The dust is sharp, charged, self-mobilizing, and toxic. It may be the single biggest obstacle between a short visit and a permanent presence on the moon. And every sunrise sends a fresh wave of it floating silently across the surface. Number 2. Lunar swirls. Look at a high-resolution map of the moon, and in a few places you'll see something that shouldn't be there. Bright, sinuous ribbons painted across the dark surface, curving and looping for dozens of miles, like cream swirled into black coffee. The most famous is called Reiner Gamma, a pale smear visible through a backyard telescope on the near side of Oceanus Procellarum. They're not craters. They're not lava flows. They have no topography at all. If you walked across one, you'd feel no ridge, no valley, no change in elevation. The pattern exists only in brightness, and after more than 50 years of study, no one can fully explain them. What scientists do know is this: every lunar swirl sits on top of a localized magnetic anomaly. The moon has no global magnetic field, but these patches of crust are magnetized, and the swirl's patterns trace the shape of the magnetic field lines below. That link isn't debated. What's debated is what the magnetism actually does to create the bright marks. The best supported idea is the solar wind shield model. The magnetic patch acts like a tiny umbrella, deflecting solar wind ions away from the surface directly above it. Solar wind darkens exposed rock over time through a process called space weathering. If the wind is blocked, the rock stays brighter and fresher. The shielded areas stay light. The exposed edges darken. You get a swirl. That's elegant but incomplete. The patterns are too detailed, too sharp-edged, and too varied for a simple shielding explanation to cover. Some swirls appear in clusters. Some have dark lanes inside bright regions. The fine structure doesn't match what models of magnetic shielding predict. A 2024 study proposed that subsurface magma, rich in the mineral ilmenite, cooled in a way that permanently magnetized the crust and created the anomalies from below. That explains the magnetism but not the surface pattern. Another idea suggests that ancient cometary impacts delivered magnetic material and swept the surface into the patterns we see. That would explain the shape, but not why every swirl has a magnetic signature underneath. None of the theories fit everything. Every one of them explains a piece and leaves the rest unexplained. That's why NASA is sending the Lunar Vertex mission, a lander and rover built by Johns Hopkins Applied Physics Laboratory, directly to Reiner Gamma. The rover will carry a magnetometer and a plasma spectrometer to measure the field and the solar-wind interaction at ground level for the first time. Until now, every measurement has come from orbit, hundreds of miles above the surface where fine details blur. If localized magnetic fields really do deflect solar wind, understanding them could help engineers design radiation shelters or choose landing sites with natural protection. If the fields redirect particles into concentrated streams at the edges, those edges become invisible hazard zones. The swirls are beautiful and strange. They're also a reminder that the moon's surface carries signatures of processes we haven't fully decoded. Something magnetized patches of a world that has no business being magnetic, and something preserved bright patterns on a surface that should have darkened uniformly over billions of years. The rover will land, the instruments will measure, and for the first time we might learn what painted those ribbons on the moon. Number 1. Lunar's surface oddities. The last images the crew sent home showed textures and shadows that didn't match familiar crater or lava patterns. Geologists looked at the photos and paused. These aren't tidy features you can file under a known category. Some patches have strange ridges. Others show smooth terraces that end suddenly. The cautious explanation is simple. Lighting, angle, and camera settings can fool an eye. The careful explanation is more interesting. If the shapes are real, parts of the moon may have experienced recent local processes we don't fully understand. Scientists are already mapping the sites, comparing Artemis images with orbital geology maps and spectral data. They'll run models that test whether impacts, ancient flows, or mass wasting can make the patterns we see. Robotic scouts or sample return missions would settle the question. The safest stance is careful work. Call it an anomaly and keep digging. The moon may still be active in ways we assumed were long over. That thought is why scientists don't stop at a single photo. They won't call it proof yet. Geologists will call it a lead. Teams on the ground are overlaying Artemis images with high-resolution maps from the Lunar Reconnaissance Orbiter. They're checking the light spectrum from each patch to see what celestials will show up. If the patterns match impact melt or volcanic glass, the case points one way. If the spectra match redistributed regolith, the answer is different. Robotic scouts are the next step. Orbital cameras can refine maps. A lander with a scoop or a tiny drill would let scientists date the site and read its history. Sample returns would settle most questions. That's expensive and slow, but it's how you actually get answers. The moon has a long memory in its rocks. Scientists will follow the evidence. They'll test each explanation until only the facts remain. The last image isn't a threat. It's a clue